All right, so the last stuff we looked at was we talked about the algebraic properties of logs, which was sort of dipping into 3.4 a little bit. And in Monday's lecture, I did a couple of examples on how to apply some of those properties. So what we're going to do today is we're going to do 3.4 and 3.5. 3.4 is just using more problems involving those properties. So we're going to work a bunch of examples. And then we'll start looking at 3.5, which is how you kind of combine all that stuff together. So this is just sort of an expansion on what we did on Monday's lecture, and I just want to work lots and lots of examples so you kind of see this stuff worked out correctly. So I'm not going to make you guys copy down all the log properties again because we did those in Monday's lecture. However, I do want to add one thing which we did not talk about. And this is the change of base formula, okay? So if you notice, if you ever actually need to get a numerical value, which we rarely will in here, but Alex will make you do it sometimes, and if you ever apply logs and exponentials in other classes, you will need to come up with a numerical value. So for example, in chemistry, you use this with pH a lot. The Richter scale is a log scale. In physics, when we talk about sound, we measure that on a logarithmic scale. So if you ever actually have to get a numerical value, if your base is E, that's natural log, you're fine. There's a button for that. If your base is 10, that's fine. That's log by itself, right? And there's a button for that. But what if it's like log base 2 or log base 3? You don't have a button for that on your calculator. So what you have to do is you have to change the base of the log into either natural log or log so you can use your calculator to solve it. So the formula works like this. If you have log base x of y, this is equal to the ratio of log of y over log of x, or similarly, sorry, natural log of e is 1. That doesn't make any sense. There you go. All right. And more generally, this. So it's equal to the ratio of log base anything you want of the thing in the inside over log base same thing, anything you want, over the original base. So the most common ways we apply this is with log and natural log because we actually have buttons for that on our calculator. But theoretically, I can change it to any new base that I want. Okay? So this isn't used a lot. Like I said, in here, we typically don't test on it. It could be on the basic skills test. So you want to make sure you're prepared for that. But this is something that you would use in a lot of other classes when you actually do logs, because if you ever deal with anything base non-10. And so we use logs a lot in statistics. Like I said, biology is going to use it, chemistry. I mean, this is the one thing that intersects pretty much all science. So the other thing I want to remind us of are the, we can kind of call this the inverse property, because we're going to use this in our algebra. So if you have log base a, right, of a to the x. So what we're actually looking at here is a composition. The outside function is log base a of x. The inside function is a to the x. So what you've done here is you've plugged an exponential into a log. So if those two bases match, then the log base a of a cancels and you just end up with x. Another way of thinking about this, well, there's a property in logs that say you're allowed to take the exponent and pull it down and make it a coefficient. So I could also write this as x times log base a of a, and log base a of a is just 1. So there's kind of two ways algebraically we think of getting to this. So when you plug a function into its own inverse, x comes out, or whatever the f of that you plugged in. So this could be, if this were x squared, it would come out to be x squared, right? So it just, the log base a of a wipes out. So since log and exponentials are inverses of each other, that means this property goes the other way. I could plug a log into an exponential. So that would look like this. If I took a and raised it to the log base a of x, that would also come out to just the x. So in the first one, I plugged the exponential into the log, and the second one, I plugged the log into the exponential. But the trick here is the bases have to be the same, or this doesn't work. Now, there is no cool algebra way to do the second one. I can't move anything, pull anything over. It's literally go straight to that. Over here, there was kind of two ways of thinking about it, but over here, this is what we have. So every property we write down for log base a, right, that also applies to natural log because all natural log is log base e, right? We just use natural log as an abbreviation. So all the rules you see apply to both. But if we're working with natural log, that means if you want to eliminate it, right, because this is base e, you would have to plug in, right, e to the x. So that would be plugging same base. This is actually the same exact thing that we wrote up here. It's just we used natural log as log base e and then e to the x. So that also means that if I take e and I plug natural log of x into its exponent, right, those are inverses of each other, it's going to come back as just x. If you don't see natural log or an actual a value written, if it's just log of x, the default is that is base 10. Okay, just like when we see a square radical and we don't put anything in front of it, right, we all default to that's a square root. Okay. All right, so let's look at some examples. And you're going to have to be real careful when you're looking at these problems to make sure you're properly seeing what's in the exponent and what is not. And you want to be real careful when you're showing your work because I have to know. It's very important, like what's where. All right, so that is log base 5. So my marker got a little crazy. So if I want to simplify this down, right? Well, if I have 5 raised to the log base 5, I should be able to wipe those two out, right? But I can't do it yet because there's a coefficient in front of the log, right? So you can't just say, oh, I see a 5, cancel, and you're done. That doesn't work like that. So you have to remove the coefficient. And so with logs, you have the ability to take a coefficient and move it in as an exponent, or you can take an exponent and bring it down as a coefficient. So I can actually rewrite this by moving the -3 in here as an exponent. So we can say, well, the first step would be this is 5 raised to the log base 5 of 8x minus 4 to the -3. Now what I have is a logarithmic function plugged into an exponential function. So these are inverses of each other. And so now I can apply this property right here, right? This says log base a of a to the x is just x. I can actually wipe out the 5 and the log base 5, and I'm just left with 8x minus 4 to the -3. And that's as good as it gets. You could, if you wanted, take it one step further and write 1 over, right, 8x minus 4 raised to the 3, because if we wanted to get rid of the negative exponent, we could do that, but I would say that that's perfectly fine, okay? Unless it says in the instructions, no negative exponents, right? Unless there's something specific in the question that tells you where to stop. All right, any questions on that? So what I wanted you to see with this first one is that it doesn't have to just be the letter x, it could be an expression. But it's whatever's inside the log function drops down. So this is the equivalent of when you have a radical and you want to get the expression out of the radical, we square both sides, makes the radical go away. Well, if you raise a log over its own base, the logs go away and the stuff inside just comes out. So we want to simplify this till there are no more logs. Basically, we want to eliminate the logs. So in the first problem, the only way we could make the log go away was to have it raised over its own base. But in this problem, since logs are the outside function, the only way I can make the log disappear is if I can turn everything inside the log to 3 to the something, because that's the base of the log, right? Because log base 3 of 3, right, would wipe out. So I'm going to have to rework the expression inside to turn it into 3's. So the first thing I see is, well, I have a 9, right? And 9 is 3 squared. So that 9, and I'm just going to play around with this expression, and then we'll go back and plug it into the log, okay? So this is 3 squared, right? And it's raised to the 2x minus 4. 27 is 3 cubed, right? And it's raised to the x minus 7. So what's the rule for a power raised to a power? We multiply them together. So that means this first term becomes 3. I distribute the 2 across to the 4x minus 8, right? And then for the second term, we're going to distribute the 3 across and get 3x minus 21. So then what's the rule I have to use now? I have to get into one single term before I can do that. So how do I combine those into one term?
Multiply.
Multiply is when you have a power to a power. We already used that. You add them, right? So if you have the same base, right, we add them, okay? So that means that then I'm going to have 3, so 4x plus 3x is 7x, and negative 8 plus negative 21 is going to be negative 29. So all of that, right, was still inside of our log. Now I can say log base 3 of 3 cancels out. So this will cancel out. And I'm just left with this. So in order to use those properties, you have to combine it into one single thing. We had to get it to just 3 to the something before we could wipe it out, right? Are any questions on this? Okay, yeah, these take a lot of practice. You want to make sure you're doing the right thing at the right time. All right, so now what we want to do is we want to expand the following terms as far as we can. So one of the things we saw when we looked at our log properties is we can combine things, and then sometimes we can split them apart. So we want to expand this all the way out as far as we can. So there's a property that says if you have log of something being multiplied by another thing, you can break it apart by saying log of the first plus log of the second. But the bases stay the same. So what I actually have here are 3 terms being multiplied together. So I can say, well, that's log base 4 of 6 plus log base 4 of x squared plus log base 4 of y to the 4th. And then there's actually one more thing I can do. I can take any exponents I see, and I can pull them down front as coefficients. So the last thing that we could do here, this will become 2 times log base 4 of x plus 4 times log base 4 of y to the 4th. So I actually can see, if this were a test question, I can already tell you that at least 2 or 3 people would make one move that they can't make And that would be on the second line, they might get to there just fine, but they'd see that last term, and they'd see a 4 in the base and a 4 in an exponent, and they would tell me that the last term was y. And it doesn't work like that, okay? It's got to be the base. If it were 4 raised to the y, right, then you'd have log base 4 of 4, right? But they would just see a 4 in the base and a 4 in the exponent, and they would just tell me it's y, right? So they just remember that you can cancel things, right? They wouldn't remember the rules of how you can cancel. So that doesn't work like that. Right? It's got to be the base. It has to match the base. Okay? So let's expand this all the way out. So we have 3 things in the numerator being multiplied together, and then we're dividing, right, all of that stuff by w to the 4th. So the rule is you add when you expand and they're multiplied, you subtract when there's division. So let's just deal with the numerator, right? So we have this, all divided by that, okay? So the numerator, things are being multiplied. So we're going to have log base 2 of x squared, right, plus log base 2 of y cubed, plus log base 2 of z to the 5th, minus log base 2 of w to the 4th. So if you were combining this into a single expression, you would read every plus sign as multiplication when you put them together, and you would read every minus as divide. And so you would just go left to right, multiply, 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 divide. We can now pull the coefficients down. It's the last step, and then it's fully expanded. So we'll have 2 log base 2 of x, right, plus 3 log base 2 of y, plus 5 log base 2 of z, minus 4 log base 2 of w. And I can tell you that most of the time, and we're going to see this when we actually go to solve problems, you're going to be combining things more than you're going to be expanding them, but it's easier to learn the expansion than it is to learn the combining first. So once you see how to break everything apart, it makes it make way more sense when we start putting stuff back together again. And so what we would do if we were solving a problem is you would see we kind of do these steps in reverse, right? Notice we break apart the numerator and the denominator. We worry about the multiplication and division. Then we pull the coefficients down. When you're combining stuff back together, you do these steps in reverse. You start by moving all the coefficients inside. Then you read the equation as pluses or multiplies, minuses or divides. All right, so let's do one more. It's a little more, let's kick it up a notch. So this is x times, and let me just write x like this so it doesn't get confused. So it's x times the 4th root of x divided by y cubed z. So all that stuff is under the radical. So since this is really a game of exponents, the first thing that I like to do when I'm doing one of these problems is if I see any radicals, I like to rewrite the equation and eliminate the radicals and turn them into exponents. It just makes it easier for me to see what's going on. So the first thing that I would do is I would say, well, this is the natural log of x times x over y cubed z to the 1/4. Because it was a 4th root. I am not allowed to pull that 1/4 out front, because the rule is it has to be the entire expression inside the log raised to that exponent. So I have two options. I can, well, really, the easiest thing to do is to split what's inside up, because what I actually have here are two different terms. I have x to the 1 times all of this stuff to the 1/4. So I can't pull the 1/4 out front in front of the log because this guy's not raised to the 1/4. Okay? So then I can say, well, I can use my multiplication rule and say, well, that's the same thing as natural log of x plus natural log of this stuff raised to the 4th. And now I could pull the 1/4 down front. So for those of you that are going to go on and take Calculus 1, there is an entire section called, because it's all about taking derivatives, but there is an entire section of the book dedicated to something called logarithmic differentiation. And logarithmic differentiation is when you take an expression that's kind of nutty, like this one, right? And they want you to compute the derivative of that, right? And that would involve the product rule, a chain rule, a quotient rule. If you, the traditional rules you've been using, it would take you 2 pages of algebra to do it the traditional way, right? But logarithmic differentiation says, well, before you start the problem, take the log or natural log of the equation, expand it all the way out like we're doing now, which is just a couple lines of algebra, and then you'll see it's very quick to go across and take the derivative of each individual term. You can do it very fast. So this will 100% come back up, and you will have to know all the algebra moves. So there is a method, or excuse me, a reason that you would want to expand stuff out like this. All right, so then what we can do is we can say, well, we need to break this apart. So one thing you have to keep in mind here, the 1/4 was times all of this stuff. So that means when we split this apart, every single one of these terms is going to have that 1/4 attached to it because it all lived inside the radical to begin with, right? So we're going to leave the natural log of x alone. I'm going to have plus 1/4 natural log of x, that's the numerator, minus 1/4 natural log of y cubed minus 1/4 natural log of z. So you can kind of check yourself to make sure that you did that right by saying, well, if I take x and I divide it, because that's a minus, right? I divide it by y cubed, I'll clearly get x over y cubed. That's pretty straightforward, right? But then if I take that fraction and I divide again by z, the z will in fact end up in the denominator, right? And so just to kind of show you, right off to the side here, if I take x and divide by y cubed, and then I divide the whole thing by z, well, that's really saying z over 1. So then you would multiply, right, by the reciprocal, and the z ends up right back in the denominator where it's supposed to. So that's why I knew, even though I had multiple terms in that denominator, I knew I just minus, because every time I divide it, it's going to end up back in the denominator. So I'm kind of done here, right? I've got an exponent I need to pull out, but notice here I have 2 terms of natural log of x. I need to combine those together. So what's 1 plus 1/4? 5/4. Get a fraction. Yeah, no mixed fractions. So 1 and it's 5/4. So we can say, well, this is 5/4 the natural log of x minus 3/4, because I'm bringing this 3 down front, natural log of y minus 1/4 natural log of z. there is an alternative way we could have done this. I could have said, gotten to here, and then I could have said, well, that's the same thing as x to the 1/4 over y to the 3/4 over z to the 1/4, right? Because we have that property of exponents that says if you have the whole entire fraction raised to an exponent, you can say, well, that's the numerator to that number, right, and the denominator to that number. And then I could have combined the x to the 1 and the x to the 1/4 and got x to the 5/4, and then I could have split up each piece, and it would have put me right back at the original problem. So, kind of, let's just call this version 2, just because I want you guys to see that there are multiple paths to get to the answer. I could have said, right, that is x to the 5/4 over y to the 3/4 times z to the 1/4, and then you can see it would expand right back out. Oops. To the same exact thing. So you could have played around with what was inside first and then expanded it, yeah.
Would it be like, is it wrong to put minus and then like a parentheses of everything in the bottom?
That is absolutely not wrong. You would, and you could absolutely do that, but you have to make sure those parentheses are necessary, because then the next step of the algebra would be to distribute the negative sign, and you would see that we end up there, yeah.
So you would have to take up the north step.
So did everybody understand what she's saying? So she was saying that if you wanted to do, oops, it's not going to help. There we go. So if you had, right, 1/4 natural log of x over y cubed z, and you didn't see that it was a minus and a minus, what you could do as well is you could say, well, this is 1/4 natural log of the numerator minus, oops, there'd still be a 1/4 here, natural log of, right, the denominator. And so what she was saying is, right, since you see those two things being multiplied, you could use the plus sign here. But the trick is you'd have to put a minus here because it's in the denominator, and you'd have to make sure you put parentheses or brackets around the entire expression. And then the very next step would be distributing the negative 1/4 across. So it would turn into a minus minus again, right? But that's kind of personal preference if you can see that move. All right. So we good here? Expanding? We did a bunch of that. All right. So now let's look at combining some stuff together. So I want to combine this into one single term. So since the last thing we did when we expanded was move all the exponents down front, now we're going to do all these steps in reverse. So the first thing we want to do now is we want to move the coefficients inside as exponents. So the very first step would be this is natural log of x to the 5th plus natural log of y cubed. So since they're both natural log and they have the same base, if I want to combine these, do I multiply or divide the terms? Multiply, because a plus meant multiply. So the next step would be the natural log of x to the 5th times y cubed, and you're done. So be careful when you're asked to combine about parentheses. So this 4 is times all of this stuff. So typically you want to kind of do your traditional rules of algebra where you go inside the brackets first and deal with that and then work your way out. So the first thing that I can see that I can do here is I want to move any coefficients I can. So I can go ahead and move that 1/2 into the x. The 4, I'm going to leave alone for a minute. And I need to move this 3 inside the z term. And then it says natural log of y minus natural log of z cubed. So that means I have to divide those two terms. So the next step, I'll just leave this alone for now. I'm going to leave the 4. And everything in the parentheses can combine into y over z cubed. So now I'm allowed to move the 4 inside, okay? But I can just put it as a 4 here, which could make things complicated. Or I know that if I have this whole fraction raised to the 4th, I'm really raising the numerator and denominator to the 4th. So I would say this is going to be the natural log of y to the 4th over the natural log of z to the 12th. Because remember, 3 raised to the 4, you multiply. So an exponent raised to an exponent. And then we've got, well, x to the 1/2 minus this stuff. So we're supposed to divide, right? But since the second thing is a fraction, right? When you divide by a fraction, you're really just multiplying times the reciprocal. So we can say this is natural log of x to the 1/2 times z to the 12th over y to the 4th. And just for right, that's what we were saying. If you divide a number by a fraction, it's the same thing as you multiply times the reciprocal of what's on the bottom. You're supposed to just kind of know that, but some people don't. They can do it with real numbers, but you throw letters in there and it gets confusing for some reason. All right, so there's one more I want to look at. So the expression inside is a cubed x to the 9 over y to the 7. So we actually have to come up with a value here for this. So they've told us what log base a of x is and what log base a of y is. So the only way I can compute the exact value of this is I need to expand that log expression so I can isolate the logs of y from the logs of x's. So since all of this is raised, or is under a fifth root, right, it's really all raised to the 1/5. So the first thing that I like to do is I like to rewrite the expression eliminating any radicals. So that's really all that stuff raised to the 1/5. So what do I do first?
You can move the 1/5 and front along.
Yeah, if you want to bring any exponents down if you can. And then we can split it apart. So with the numerator, we have two terms being multiplied. And remember, the 1/5 is going to get distributed all the way across here because everything was under that radical. And then we're dividing by the single term in the denominator. So a cubed times x to the 9th divided by y to the 7th. You can always kind of check your way across, make sure you did it right. So I still can't plug anything in yet until I get rid of those exponents, because I don't know what log base a of x to the 9th is, but I know what log base a of x is by itself. So the last thing we want to do is bring down any remaining exponents. So we're going to have 3/5 log base a of a plus 9/5 log base a of x minus 7/5 log base a of y. So what's log base a of a? Right, 3/5, right? So it's 1, right? But the 3/5 is out front. So this is 1, and another way you can remember that too is that's really just a to the 1, so it just comes back as itself. So the first term is 3/5, right? Then we have 9/5, and log base a of x we were told was 4, right? Minus 7/5, and log base a of y was -3. So fortunately here we have a common denominator all the way across. This gets nice. So 3/5 plus 36 over 5 plus 21 over 5. And so that's going to be 57. So we get, it's minus times a minus, so it's plus. So it's 57 plus 3. It should be 60 over 5. And then the answer is 12. Make sure I did that right. 56, 57, yes. And so it all simplifies into 12. All right. We good? Okay. So since we know that logs and exponentials are invertible, right? We actually kind of know what their inverses are. We can actually compute the inverses using these algebraic properties of functions that we couldn't really do that before. So if it's just a to the x, right, or just log of x, we kind of know what the inverse is. But what if we want to shift or slide the graph around? It's still invertible, right? We have to be able to compute the inverse of that. So the way we said generally that you find an inverse, right, is you rewrite the expression switching x and y, and then you solve the new expression for y. So now that we understand how to work with logs and exponentials algebraically, we can now compute inverse functions involving them. So the first one I want to look at is f of x equals 2 to the x, right, plus 7. And we want to compute the inverse of this. So the very first thing that we do is we want to switch x and y. So I'm going to rewrite this as x equals 2 to the y plus 7. And then I'm going to solve this new expression for y. So I want to get y by itself, so I'm going to leave the 2 to the y on the right, and I'm going to subtract 7 from both sides. And the only thing that will drop that y down and make it just y by itself is if I take log base 2 of 2 to the y, right? Because that will cancel out the 2 in the base and drop the y down. But whatever you do to the left or right, you have to also do to the left. So that means this is going to be log base 2 of x minus 7. And I'm going to take log base 2, of 2 to the y. And so this will cancel. And there's your inverse function. All right, we're going to look at one more real quick. So because we have an e here, this means I'm probably going to use natural log, right? So the first thing I'm going to do is I'm going to say, well, this is 6e to the y plus 4, right? Minus 9 equals x. And now I'm going to solve this for y. So I'm going to get that 9 out of the way. So we'll say 6e to the y plus 4 equals x plus 9. Then I want to get that 6 out of the way because I can't take the natural log until it's just e, right? So e to the y plus 4 will equal x plus 9 all divided by 6. And now I can take the natural log of both sides. So the natural log of e to the y plus 4 will equal the natural log, right, of x plus 9 over 6. So on the left side, the natural log wipes out the e, and I just have y plus 4. And then to solve for y, we'll simply subtract 4 from both sides. So this 4 is on the outside, and this is our inverse function.